So let's go through a few of these types of models and understand why they are relevant and how we must be using them. I will just say it outright, the mixture and species types are going to remain the same for our purposes. I'll not discuss them in detail. Once we get to multi-phase flows, we can discuss it a bit. Let's start with thermo. This helps explain what the fitting functions are for calculating your specific heat, enthalpy and entropy. Ranges from absolute values to sensible values and also the Gibbs free energy explained later. These properties change with temperature and we require good models to explain how they change. The way we do it is by providing tabulated data with coefficients and ranges of temperature to help the solver calculate these properties on the fly. Let's talk about the equation of state now. This is a fundamental mathematical relationship that talks about the connection of state variables of a substance. In a sense, we calculate the value for density and validate it with the equation of state. Of course, there are different models available and we can choose a relevant one based on the level of complexity we are going for. Ideal gas or perfect gas, as is called in OpenFOAM, is the most commonly used one. Coming to transport now, this is strictly about the relationship of how viscosity and thermal conductivity change with temperature. There are models ranging from Sutherland to polynomial fits to logarithmic polynomials. They also provide a way for on-the-fly calculation of these properties as temperature changes, and it's quite necessary for accurate simulations. Finally, we have energy. This helps explain what variable we want to use for solving the energy equation. What does that mean? The energy equation is a balancing equation that talks about how energy enters your domain and how it leaves. The equation can look something like this, where E is specific internal energy, or it can look something like this, where capital E is total energy that accounts for kinetic energy per unit mass. And as I said before, mixture and species types are just going to remain constant. We are not changing them. So let's move on to understand how OpenFOAM does it. This right here is the thermophysical properties file. We can see entries inside the subdictionary. We have entries for type, mixture, transport, thermo, energy, equation of state, and species. Type talks about the type of thermodynamics we use. The HE thermo model primarily talks about compressibility of your working fluid. This model treats temperature and pressure as its fundamental independent variables for defining the thermodynamic state, and when solver provides enthalpy from energy equation and pressure from pressure equation or continuity, HE thermo directly calculates temperature as a function of enthalpy and pressure. This is standard thermodynamic equation. Once T is found, it calculates the density from equation of state, and then it calculates compressibility psi based on temperature. Why psi? Well, it makes life easier with compressibility related to density. And this model specifically is for gases where density is calculated by the formula. So either we have HE psi thermo or we have HE rho thermo, which works in a pretty similar manner with emphasis on density. It still operates in solver where H and P are primary salt fields from which T must be derived. Its internal formulation conceptually gives density a more central role alongside temperature for defining the state. This model is less commonly used when compared to HE psi thermo. Please note that HE psi thermo is not necessarily built for liquid fluids. Both these models are trying to use compressibility to solve for temperature field. Liquids are nearly incompressible, while rho thermo conceptually emphasizes density. HE psi thermo is more robust and standard choice for gas phase thermodynamics. This model handles air, oxidizer, fuel after it evaporates and becomes part of gas mixture and the products of combustion. For liquid combustion, it is advisable to use Lagrangian framework for liquid droplets and then compute the Eulerian framework of gas phase using HE psi thermo anyway. Next we have mixture. This describes the mixture type, essentially tells OpenFOAM that the fluid you are simulating is composed of multiple distinct chemical species. Overall properties of this mixture depend on the properties of each individual species and how much each is present in this mixture. When chosen, OpenFOAM expects you to define list of species, how the thermodynamic properties of each individual species are calculated, also how the transport properties are going to be evaluated. The multi-component mixture type works as a mass fraction weighting of transport and thermo properties. What does that mean? Well, mass fraction weighting is a common method to capture the overall property of the mixture based on properties of individual components and their relative abundance by mass. So the sum of all the individual species would just result in the mass of your substance. Similarly, the mass fraction Yi is the mass of that species I divided by the total mass of the mixture in a given volume or sample, and the sum of Yi should be equal to 1. The idea is that each species contributes to the overall mixture properly in proportion to how much mass it represents in the mixture. Weighting here just means we multiply the mass fraction with the property, and if we choose to find the mixture property, we just need to add all up. This works for specific heat, enthalpy, energy, etc. Now let's come to the drawing board a little bit and imagine I have this reaction with me. Nitrogen for the most part is inert, and assuming that this is occurring in a single computational cell at a temperature of 1500 kelvins. So at this specific point in time and location, the mass fractions could be something like this. Notice that the sum of all is equal to 100% or 1.0. Now there are other models that are available, something called the value multi-component mixture, which does the mole fraction weighting. And also there is the Wilks model, which also does mass fraction but uses the Wilks equation for calculating transport properties, often used where molecular size differences are quite large. Stick to mass fraction weighting, it makes life easier for combustion simulations. Next we have transport. This describes how viscosity, thermal conductivity and species diffusivity are calculated. Sutherland is the most commonly used model as discussed before. This model assumes that viscosity and thermal conductivity are temperature dependent as shown in this formula. AS, TS are model coefficients to be defined for the fluid you are using. There is also the polynomial or log polynomial models with their own set of coefficients. The simplest model is the constant, which assumes constant viscosity and Prandtl number. Now Sutherland works for the most part. Use polynomial fit when possible when you have the experimental accurate data. We discussed before the kinetic theory of gases. The model proposed along with this theory is not included with OpenFOAM, that is, viscosity and thermal conductivity are related to square root of temperature. Also they are independent of pressure for simple hard sphere model. Other models include the Andrade, ICO tabulated, and WLF. You can find information about these readily on this particular website under the classes, class list, foam or the .h files. Talking about thermo, this is not really a model, so to speak. Instead, this is a way of representing the thermodynamic data for individual gas species. This includes data for calculating specific heat, enthalpy and entropy. Take JANAF for example. It contains data about coefficients to calculate the specific heat, enthalpy and entropy, something that looks like this. We can see something like the T low, T high, T common, high CP and low CP. The general advice would be to use JANAF. Let's take an example from before. Assuming we use JANAF polynomials, OpenFOAM finds the specific heat for each pure species at temperature T is equal to 1500. Assuming these hypothetical values for our purposes, the mass fraction weighting makes it so that specific heat mixture is a mass fraction weighted sum. Note that this value will change if you make changes in the amount of matter of reactants. Also it will change if temperature changes. And we have these other models. Now speaking of energy, this explains the specific usage of thermodynamic variables for thermotype. OpenFOAM solvers that handle energy transport for compressible, heat transfer or combustion flows actually solve the conservation equation of energy. This equation can be mathematically formulated in different ways using variables like internal energy, enthalpy, total energy and total enthalpy. This energy entry specifies the fundamental thermodynamic state variable that the library will now use to relate other properties, particularly temperature. For instance, if you choose sensible enthalpy, we will calculate H_S from T using CP specific heat. Sensible enthalpy talks about heat energy that causes changes in temperature during flow physics. The sensible part talks about the portion of total enthalpy that is directly associated with the temperature of substance and not just expansion work. This is calculated using integration of specific heat capacity at constant pressure with respect to temperature. So why use it? In many fluid dynamics problems, especially single phase gas flows, even reacting ones, the changes in sensible enthalpy is directly related to the heat added or removed that causes temperature changes. The energy equation is often formulated naturally in terms of enthalpy, and the chemical energy, heat of formation, is typically handled separately. The change in total enthalpy during a reaction is calculated based on the difference in heat of formation between products and reactants. The sensible enthalpy then simply focuses on thermal state before or after reaction's energy release is accounted for in the source term of energy equation. The other models include these. So with equation of state, as previously discussed, it's a fundamental mathematical relationship that connects the state variables of a substance. Perfect gas is often used, which is the P is equal to rho RT model, which essentially assumes no intermolecular forces, and it's a good approximation for low pressures or high temperatures. It is advisable to use the Peng-Robinson model for real gas modeling. This model aims to improve upon the ideal gas law by accounting for two major factors: finite molecular volume, intermolecular attractive forces. The equation is more complex than the ideal gas law, typically written in terms of temperature, pressure, molar volume, and substance-specific parameters A and B. It's a cubic equation with respect to the molar volume of compressibility factor. Looks something like this right here. The parameters with the C subscript are essentially the critical parameters. Finally, the other models include these. So in summary, we discussed the kinetic theory of gases, where we went on a discussion on the molecular level. We expressed what your pressure, what your temperature looks like. We also understood what viscosity and what the thermal conductivity could look like. We also understood the need for modeling and the different thermophysical models that are present in OpenFOAM, namely the mixture, transport, thermo, energy, and equation of state. In the next video, we'll talk about the combustion models in OpenFOAM. Until next time. No.